Okay, let's begin. Hello, everybody. Welcome back. On Friday, we were talking about curves, and I talked about the vector form of the parameterization of the vector expression associated with a parameterized curve. And one can think very generally about this problem, but I like to think about it very specifically, where t is the parameter, it is time, and r tells you where you are at what time. That's straightforward. And r is a vector. And what do I mean by that vector? R is the position vector. If I have an axis x, y, z, r is the position vector of a point on the curve at any particular time, r of t. Okay? So that's r. I draw arrows on the curve to indicate a direction of motion, a sense of going across the curve from one direction to the other. In physical problems, of course, objects have trajectories. But just for a pure curve, if you just drop it down, right, there's no sense of direction. You might be left-handed and draw it this way. You might be right-handed and draw it. I just did the same way. Anyway, so you might do it whatever, either way, okay? So the curve itself doesn't necessarily have a sense, but it acquires a sense of direction when you parameterize things. Because this, for example, is the increasing. If you're going this way, then you're increasing x with time at this time. At this time, x is increasing, and so that gives you a sense of direction. Okay? This is the form that we'll basically use the most in this section. R of t is a function x of t I hat plus y of t j hat plus z of t k hat. I talked about its time derivative dr dt, and what I mean by that is simply dx dt I hat plus dy dt j hat plus dz dt k hat. And I emphasized that another word for this is the velocity v vector. And v vector can be any vector field, any vector can be represented either in terms of components on a basis or magnitude and direction. And so v vector can be represented as the magnitude of v multiplied by the direction vector in the direction of v divided by the magnitude. Sorry, there we go. Oops. So I'm just splitting this up. I haven't done anything. I've just said this is the magnitude of v, and I multiply and divide by the magnitude of v. This combination is a unit vector. This combination is a unit vector, which is called v hat. That is to say, it's a vector in the direction of v, but with length 1. And so all the length is carried by the magnitude of v. And this vector has a name also. This is the tangent vector, and we will be using t hat to denote the tangent vector throughout this section. Okay? So I think I talked about, let me finish this. What is the magnitude of v? The magnitude of v is, by Pythagoras' theorem, dx dt quantity squared plus dy dt quantity squared plus dz dt quantity squared, all to the power of 1/2. So the square root of this. Okay? And I could write the direction vector out too. It's just a bit of algebra. It's not a big deal. You can figure that out. Very well. So we talked about the line last time, and I talked about a couple parameterizations of the line. Is that correct? Please remind me. Last time, a couple times ago, 5 days ago, which is ancient history now. Okay. I want to give you examples of two curves. Hold it. Did I do the circle also? Did I do the clock? I did do the clock. So I did the clock and the line. So we're good. Oh, I can stop there. Why am I going back to this? The clock and the line. So let me just remind you. Let me remind you the line. Okay? The simplest parameterization for the line is the linear parameterization. And I'm going to write the parameterization for a line, r of t, is very simple. It is, I'm going to write it u times t I hat plus, actually I'll factor out the t just to emphasize something. u I hat plus v j hat plus w k hat, all multiplied by t, plus x0 I hat plus y0 j hat plus z0 k hat. This is a general parameterization for a line where I've used a linear function. So you look at this very quickly. I use UVW. By the way, this is a convention in fluid dynamics for a velocity field. So it's good to have UVW. You will see this in engineering classes. U is the x component of the velocity field, v is the y component, and w is the z component of a velocity field. And the reason I'm doing that is because this looks like a velocity field. At time t equals 0, this line is at the point x0, y0, z0. As time t increases, it's going in this direction. What is the velocity vector, the magnitude of dr dt, or yeah, just the magnitude. Let's not do the magnitude. Just the velocity vector is all of this stuff in parentheses. This is the velocity. So that was the line. And there's also the circle we talked about. And I said the circle r of t is equal to, I did a capital R for the radius of the circle. And I said cosine, let me call this r of, yeah, why not, r of t, cosine 2 pi t over the period I hat plus r times the sine of 2 pi t over the period j hat. Now this is a circle. This is not the clock. This is not the clock, right? The clock we recognize, this is a circle that in the case that capital T is positive and little t is increasing, this is being traversed counterclockwise, right? So I wrote the clockwise circle last time. Nonetheless, this is a circle. It's not the clock. Okay, so those are a couple of examples from last time. These are really important examples. Okay, these are really important examples. I think I parametrized. Let me. Did I do the parabola yet? Did I do a parabola yet? Okay, so let's do a parabola. Let's just fun with a parabola. Let's put a parabola in R2. Okay. So how would I do this? Parabola in R2. Now, if I were to write the equation for parabola y equals x squared, everybody would nod and say, yeah, that's cool, that's good, right? But you know me, I like to have parameters in this problem. I don't want just this parabola that goes through the point 1, 1. I want a parabola that I can control, that I can change a little bit, to understand when I change it, what happens, okay? So I like to have the parabola maybe go through the point. Let's say we're going to have a parabola whose vertex is at the origin, who is opening upwards. Okay, so I've already restricted it with two statements. And then it's going to go through a point, let me call this point A and A comma B. Is that okay? A comma B? Okay, so it does not satisfy this equation. No, it satisfies something more complicated, quote unquote. And that equation is y over b is equal to x over a quantity squared. You notice how quickly I got that down, and think about how quickly I got that down when y could write it down so quickly. Notice when x is equal to a, the right-hand side is 1, and when y is equal to b, the left-hand side is 1. So clearly it goes through that point, and it goes through the origin, and it opens upward. So it's got to be the right parabola. So if I write that out, it's y is equal to b times x squared over a squared. So there's this parameter, this combination, which the denominator is a squared over b. And you know, I like to emphasize units. The units of that, well, if x is a length and y is a length, it's like a height, an increasing parabola, some sort of shape you've made. A is a length and b is a length. So this combination is a length. It's length squared over length. It's a length. So that's the length that pops out of this whole problem, okay? So I could simplify this notation by just calling this L. I'm going to call this x squared over L. And you now see that if L is equal to this, it goes through the right point. Now I'm going to just talk about L. Okay? So this is a one-parameter shape. Now this is the explicit form of the parabola. I'd like to make a parametric form of the parabola. Okay? Yes? You tell me. That way L's in the denominator. I don't have experience. It's hard to, no, I have experience with inverse lengths. When you tell me what an inverse length is, I know I would call it a wave number, right? I call it a rate, but I don't think you guys have experience with inverse lengths. So before I force you to have experience with inverse lengths, I say, oh, you have experience with length. So if I show you where the lengths appear in this problem, maybe that'll relate to something that you have experience with. That's my answer. Good thinking is not just going through a calculation. It's also having good taste. Okay? Having good taste is very important. I don't think anybody's taught you that in mathematics, that you want to have to have good taste. Good taste is knowing when it's appropriate to factor an expression, because that will convey more understanding, and when it's appropriate to distribute the expression. So the question is, how do you develop taste? With a little bit of experience. All taste comes from experience, right? As college students, you're known to have no taste, but eventually you get some taste. Yeah, look who's talking, the guy who dresses in black shirt and jeans every day. Okay. So that's why I do that, okay? Does that suffice as an explanation? Very well. Where am I going? I want a parametric form of this curve. Do my sleepy students want to suggest a parametric form? I don't call on you a lot because there's always that blank stare and that awkward us looking at each other. Avoiding eye contact. Look down. He's scoping the room. This side is scared. Yes? So a very straightforward parameterization is to allow x to be equal to t. Okay? Now, then you're saying, well, meters is equal to time. Well, like I said, there are multiple parameterizations, right? And we don't have to think of t as being time. But nonetheless, x is equal to t is a good choice here. Why is it a good choice? This is an open object. This object is open. And if I allow t go from negative infinity to positive infinity, it traverses the whole domain of dependence of this object, which is useful. Okay? Furthermore, so I'll get the whole domain of dependence. If I let x be equal to t cubed, it would work also. But if I let x be equal to t squared, it wouldn't work because I wouldn't be able to get negative x's. Okay? If I were to let x equal sine t, it wouldn't work because I wouldn't be able to get x's that are bigger than positive 1 or less than negative 1. So that's how you have to think about how do you choose your parameterization. In general, you'll try to choose the easiest one, which is x equals t. So choose x equal t, and then you substitute sub into the y equation to y equals x squared over L, and that implies that y equals t squared over L. And so if I were to write my r of t, that's equal to t I hat plus t squared over L j hat. That is the position vector as a function of time. Notice that at time equals 0, it's at the origin. Okay? So I would draw it as such. Here's the parabola. Okay? Here's A and here's B, and we said that L is E squared over B, A squared over B. And at time t equals 0, you're over here. And at some other time, you're over here. This is r at, oh, here's a good question. What time does it reach this point? R at t star. What is t star? One? Think again. A. Because when t star is equal to A, r of t star is A I hat, which means that gets you over there, plus A squared over L j hat. But A squared over L is B. So it's right there. Okay? So that t star is equal to A. Okay. Now, we can calculate things about this. How about the tangent vectors? Okay? Let's calculate the tangent vector. So the velocity. What's the velocity vector here? Well, it's dr dt. So dr dt is equal to, well, I've chosen the simple parameterization. So when you take the time derivative, I hat and j hat are constants. the direction that way is always that way. The direction that way is always that way. Okay? That's not always true if you go around the Earth, right? Up is moving around. Okay, that's why we don't use I hat to denote up on the Earth, really. Nonetheless, let's say I hat and j hat are constant. We create them as in a R3. I hat is to the right, j hat is up in the y direction. That means when you take the time derivative, you're not taking the time derivative of I hat. It's just a constant. Okay? But you are taking the time derivative of the prefactor, which is 1. So the time derivative is 1 I hat plus 2t over L j hat. And this is the velocity of this trajectory. Sorry, I should not put my hand there. Of course, the magnitude, dr dt, is straightforward. That's 1 plus 4t squared over L to the 1/2. I just did this squared plus this squared. Oops. I saw some eyes, so I made a mistake. Somebody caught my mistake in the audience. Yep. And so this is the velocity. And let's take a look at the velocity for a second. At t equals 0, the velocity is 1. And we can see, well, we'll see the direction in a second. As t gets larger and larger, the velocity gets larger and larger. Right? In fact, as t gets very large, this term is much bigger than this. And the velocity goes to, well, you can approximate it for large t as approximately equal to that, which is 2t over L. That's the velocity, goes to 2t over L. Okay. Now, the direction vector v hat is equal to 1 I hat plus 2t over L j hat divided by this velocity. And I'm going to write it out. I'm not going to do this often, but once in a while it's useful to think about it. So this is the parametrized velocity, okay? Now, this is a little additional. This doesn't appear in the book, so let me just make this little additional thing, okay? Number 1. Since the parameterization is so easy to invert the parameterization. Why would I want to invert it? Well, this is the direction, right? This is the direction over here. The velocity divided by the speed. This is the direction. And it's a function of t. And you're like, oh, well, what does that mean? I mean, what does that mean? Well, how about I write it instead by letting t equal x? That is to say, I made x equal t up there, which defined the parameterization. But now let me remove t in favor of x. And so that tells me the direction vector is 1 I hat plus 2x over L j hat divided by the square root of 1 plus 4x squared over L squared. This is just a fun thing to do, in my opinion. It's a fun thing to do because you know where, you have a sense of what x is a little more naturally. Of course, t is equal to x, so you could have just done it in one fell swoop. But nonetheless, this is the direction vector as a function of where you are in x. Okay? So that's good to note. But there's another thing I want to tell you about. And I don't know if they say it explicitly in the book. And honestly, I was not told this when I was first learning calc. And so I feel like I have to tell you. Okay? So here's the parabola. I'm going to make a dashed line over here. Okay? Let me make a dashed line over there. And at some point on the parabola, let's say right here, this is the unit vector. Let me say that's unit vector v hat. And at some other point, let me say that's unit vector v hat. Okay, this is v hat at x equals 0, and this is v hat at some value of x. Okay? You can imagine yourself walking around, right? And all you see is, oh, I'm looking at Sacramento, or I'm looking at the Mount Lassen. Which way am I looking? Okay? So all you see is the angle that you're looking at. So in fact, you realize that you could look at v hat. Since it's a unit vector, you can really think of it as having some angle. And let me call this angle alpha. Okay? The angle from the horizontal. Does that make sense? It's the angle from the horizontal. When alpha is 0, you're over here. As alpha increases, you're pointing up. Okay? So you can imagine v hat of x. Well, it's a unit vector. Its x component, therefore, is the cosine of alpha. And its y component is the sine of alpha. If it's a unit vector, it must satisfy that this is the sine of alpha, this is the cos of alpha, and this is 1. Sine squared plus cos squared is 1. Okay? So v hat of x is equal to the cosine of alpha. But of course, alpha must depend on x. Right? The cosine of the angle, alpha angle, that you're pointing in as a function of where you are, I hat, plus sine of the angle you're pointing in as a function of where you are. And so now we see that we can write, oh, cosine of alpha is equal to that first term, 1 over the square root of blah, blah, blah. And the sine of alpha is equal to 1 over the square root of blah, blah, blah. No, not 1. That's a 2x over L. And so that we realize if we take the ratio of these, we see the tangent of alpha of x is equal to sine divided by cosine, which is this divided by this, which cancels that square root, and you're left with 2x over L. Which tells you that alpha of x, the angle you're pointing in, is simply the arctan of 2x over L. Which is a really simple expression. It's really a simple expression. What would it be for a circle? Question. What is alpha of x for this circle? Think about it. What happens alpha of x? This is a nice and simple expression. Arctan. It's about as simple as you can get. It's arctan. So arctan is related to this parabola, to the tangent of the parabola. I saw a hand over here.
I just realized what it was.
Okay. Anybody else? Okay, so that's what I wanted to talk about regarding curves. I actually want you to figure this out for yourself. It'll be very edifying. Do you guys see the large eraser? Did I lose it? Thank you. I'm losing it, but not this. I'm losing that. Can't see anymore. Okay. Very well. There's a comment to make. So there's basically in section 13.1, curves in space and their tangents, they talk about how you can deal with vector-valued functions of time. So for example, in 13.1, they define the tangent, define the velocity field, etc. But they also define the acceleration. And you guys have been in this business long enough to know now that the acceleration, a vector, which is a function of time, is simply the is the first derivative of the velocity, which must therefore be the second derivative of the position. All of these are functions of time. Okay? And we're going to talk about the geometry of acceleration when we get into curves, when we get study properties of curves and curvature before the end of this section. Okay? But one of the things they want to talk about is let's just learn some basic calculus operations. Let's just do some basic operations on vectors that are functions of time. So e.g. And these are just the rules, e.g. Say you are given two vectors, two vector functions of time. Okay? So now they don't have to be position vectors. They're just, let's say there's A of t and B of t. These are just two vector functions of time. How would you calculate d by dt of A of t plus B of t? Well, you can do two things. You can add those vectors and differentiate them, or you can differentiate those vectors and add them. This is differentiate first and then add. This is add first and differentiate. Well, we know that if you had two functions of time, you could differentiate first and add first and differentiate. Those operations commute. Vector valued functions of time have the same property. And it's simple to show. I effectively showed it at the beginning when I discussed what R of t, like R of t had a representation in terms of I hat, j hat, and k hat. Okay, so that's an easy one. But another thing that you can consider is what is d by dt of A of t dotted into B of t? So when you take two vectors and two vector functions and you dot them, dot product takes two vectors and creates a scalar function, just a function of time, which is this dot product. Okay? And the dot product creates the shadow, right? As we talked about. Was your hand up, or it's okay? Yeah. No, raise them up high if you want to talk to me. So the question is, what is the time derivative? Well, we have product rule, right? We have product rule. And if you take a look at the components of A, let me say, A has a component A1, A2, A3. Is that okay? I'll use A1, A2, A3 for the I hat, the j hat, and the k hat component. And B has components B1, B2, B3 for the I hat, j hat, and k component. So if you take this dot product, the dot product results in A1, B1 plus A2, B2 plus A3, B3. And then I have to take the time derivative of this. Well, if you take the time derivative of this, you realize you first have to split it up into the sum of derivatives, and then you have to use product rule on each of these. And when that all comes out of the wash, when it all comes out in the wash and you do this, and I'm not going to do it, it's too easy to do, and it's something you should do and you should read in the book, this results in the product rule for vectors, which is the time derivative of the dot product is A dotted into the time derivative of B plus B dotted into, well, maybe I'll say the time derivative of A dotted into B. That way we keep A, B, nice order. Aesthetics, taste. Okay? So this is true for dot product, and then there is a similar rule for cross product. Okay? So you should go and convince yourself of all these rules. And they fall out of the definition of a vector and the definition of the derivative. And the properties of the derivative which arise from the definition. A derivative is simply subtraction and division. Okay? With limit. Okay. So that's all I'm going to say about chapter 13.1. I would like you to read 13.1 if you could. Okay? (13.2) Eraser. Chapter 13.2. projectile motion. Newton invented the differential calculus to deal with the problem that I'm about to deal with. So this is the raison d'être, right? So this is important, but we had to build up a lot of things here. We had to build up calculus, differential, and integral. We had to learn about curves, okay? You had to spend years doing algebra. So in some sense, this is a big punchline here, okay? The projectile motion is a big punchline. Now, who of you have done projectile motion in physics classes? Okay. So let me ask, who has not? Okay, don't feel shamed. It's okay. So since you guys have done projectile motion, I can skip this, right? You guys are particularly quiet today. Maybe you're always this quiet. I'm just particularly low energy. Was it the exam? Was it the exam? Let's not talk about it. Okay, projectile motion. So when we do projectile, let's do some projectile motion right here. I'm going to do projectile motion, not with just gravity. We're going to think of a baseball thrown in the air under the force of gravity. Okay, who's done that problem before? So that's boring, right? It's like, bam, you got it, right? Those of you who haven't done that problem before, that problem is going to be done as a subcase of a more general problem. Because everybody knows that a baseball is not acted upon only by gravity, but it's also acted upon by drag forces of air, okay? So who's done do you guys do the drag problem in physics class? Good, so I can teach you something new. Yay, what?
We've done drag, but it's only an instantaneous point for velocity. It's never at a dynamic velocity.
Oh, yeah, I know. And you know, that whole drag problem was part of the reason why Aristotle had the wrong relativity in his mind. Because there's always drag on an object. So he thought, you know, anyway. Let me just jump into it. A equals F over M. Newton's second law. A body in motion will tend to stay in motion unless acted upon by an external unbalanced force. The acceleration, the rate of change of velocity is proportional to the force divided by the mass of the object. Okay? This is the basis for all of our mechanics, and this is the problem I'd like to solve right now. So, Newton's law, e.g., throw a baseball. Okay? Throw a baseball. So F is going to consist of two forces. Gravity and drag due to air. Okay? So, what is F? F is F gravity. So let me call that Fg plus Fd for drag. And I want to look at each of these separately. Galileo gave us Fg. Galileo gave us Fg. Galileo's great insight was to realize that Fg, the force of gravity, is proportional, or rather, Galileo's great insight was to recognize the acceleration for different objects is the same. I don't think he thought in forces. He didn't think in forces because Newton thought in forces. So the acceleration for different objects is the same. So here we have my eraser, and here we have my chalk, and I release them, and they indeed do land at the same time. So if the acceleration was the same, what we say is that this acceleration of gravity, acceleration, is equal to downward, which is the negative k hat direction, times some constant. And we use g to denote that constant. That constant is measured pretty readily at 9.8 meters per second squared. But as you know, I will always call this 10 meters per second squared because I don't mind a 2% error. Okay? So if the acceleration is constant, that implies the force of gravity, going back over here, if the acceleration is the same for all different objects, that means the force of gravity must be proportional to the mass. Okay? So that means the force of gravity is equal to the mass of the object that's being acted upon multiplied by this constant times k hat in the downward direction. That's a profound fact. That's a profound fact. Prior to this, people philosophized, I don't know if people who actually dealt with it knew this probably, but people philosophized that the force should depend on the mass. Sorry, the acceleration should depend on the mass. Different objects should accelerate at different rates. Okay? And the reason is, of course, it's hard to have different masses with the same shape, and you do something like that, and you see that these two objects fall at different rates, and in very different ways, in fact. Okay, so this is the first one we have to deal with. And you guys are all grown up now, and you've done this in your old hat and all jaded about all of these issues. I still think it is beautiful. Drag. You know that our previous misunderstanding of how the force of gravity worked was because every time we launched an object in the force, under the force of gravity, there was this other force acting on it, which is drag force. So what is FD? Now, I'm going to tell you something. FD is ridiculously hard. Okay? Drag force is the subject of fluid dynamics. It is a huge question still in aerodynamics and aeronautics. It is a major question still. Because when an object goes slowly, there's one kind of drag force. When it goes faster, there's another kind of drag force. And when it breaks the sound barrier, there's a whole other set of drag forces. Okay? So the drag force is a super complicated function. And so it's ugly. Ugly. It's called engineering. And by ugly, I mean, you have to be brave to dive into something like this. Okay? As engineers are brave. Okay? They do it because they're brave. Okay? So this is, it's ugly, it's engineering, and therefore it's important also. Okay? All this beautiful stuff is not as important as the ugly stuff. Okay, let's talk about the drag force. Okay? So the drag force, what do we expect of the drag force? FD, well, if the object is stationary, it should not experience a drag force. So FD should not depend on position. Okay? So FD should only depend on velocity. Right? And what we notice is that FD should be proportional to negative, so if FD, let me not say proportional, should act in the opposite direction of V. That's pretty clear, right? If I go this way, the force of the air is tending to force me that way. You know this when you're trying to bike and you're late for a class, right? When the wind is stationary, let's not worry about the headwinds. Just even when the wind is stationary, you're biking into the wind. You feel the force behind you, okay? So it should act in the opposite direction of V. Okay? So how do we do this? Well, we write FD is equal to, well, let me say negative V vector over magnitude of V. I'm just going to write it that way. Because that's a direction, right? There's opposite direction of v, times some crazy function. And so let me call this little f, which must depend on the size of v. This crazy function depends on the size of v. Make sense? So, you know, I wasn't going to say this, but I'm going to say it. So, this is a function. This is engineering. Everything from here on out is engineering. What do we know about f of v? We know that little f of 0 is equal to 0, right? Because when it's not moving, the drag force should not, there should be no drag force. What else do we know? That's about it. That's about it. Okay? So if we were to write little f of magnitude v, like say just draw it, and since magnitude v is positive, I'm going to draw it like that. I guess we know f of 0 is 0. We know f is greater than 0. Maybe greater than or equal to 0, clearly greater than or equal to 0. This is magnitude of v. And we know that f of 0 is 0. We know that it's got to just kind of go like this. It starts to go like that. Yes?
It seems like we get into like this recursive series of just never getting out of it because any v's past instance 0 is going to depend on the v at the time.
That's exactly. So yes, exactly. I mean, so you're articulating the issue with differential equations in the first place. So I'm telling you that what a differential equation is going to say is the time derivative of the velocity is going to be proportional. We'll find that it's proportional to the velocity. We'll find that in a moment. Okay? So you're like, what? How do you solve that problem? Well, actually, that's what the calculus was all about. That's exactly the question. It's like, how do you solve this problem? That was a whole new concept in the 1690s, right? And that's why he invented the calc. So I will show you how to get to that, okay? So all I'm saying about this, everybody, and this is f of magnitude v, all I'm saying about this is the only thing we know about this function is that it's positive, it only exists for positive values of argument, and it goes to 0 when its argument is 0, okay? In fact, engineers actually know that this function curves up in some crazy ways, okay? It has some weird divots in it and all of that stuff depending on the shape. We know that it would depend on the shape, but given a fixed shape, all we know is it goes up, okay? So what's the best thing to do? Taylor series. It's such a joy to teach you all. You're going to be like, yay, he's given me a reason to like Taylor series, right? No. Well, okay, I will do the Taylor series expansion of this. I will do the Taylor series expansion of this thing. You're not going to mind. It's not that hard. So let's imagine f of magnitude v is equal to f of 0 plus the derivative of f with respect to its argument. Derivative of f with respect to its argument, I'll call that s, evaluated at magnitude v, evaluated at magnitude v equals 0, times the magnitude of v, plus dot, 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 dot. I'll just do two terms in the Taylor series. See, engineers, why did you learn Taylor series? You didn't learn Taylor series to worry about infinite convergence issues. You learned Taylor series because a couple terms in the Taylor series give you a decent approximation to a function. That's why you learn Taylor series. You do Taylor series, you're like, oh, I'm just going to guess a few terms in the Taylor series. I get a decent approximation of the function. That's good. Okay? Every function is nearly constant in a neighborhood, sort of linear, a little bit of quadratic, some cubic, good enough. In fact, I'm just going constant linear. And I'm going one step farther because I know that f of 0 must be 0. And this is just some number that you will measure in your laboratory. And so this is I'm going to call this number, what do I want to call the number? I want to call the number C. It's called the drag coefficient. Coefficient of drag multiplied by the magnitude of v. plus, I don't know, complicated things, depending on whether the wings are bumpy or whatever they're doing. And therefore, coming back over here, the force associated with the drag is approximately equal to negative v vector. Magnitude of v divided by magnitude of v is 1, and I have the drag coefficient out here. This is an approximation to drag. This is an approximation. This is the lowest order approximation, and in fact, it's good. It has to be good, because it must be good, because it's a function, and this is the Taylor series expansion of the function. It's definitely a good approximation for v being small. Now, what do we mean by v small? That depends on the case you're dealing with, right? V small in honey is a lot different than v small in air, okay? So there's a whole fluid dynamics that deals with that. But I guess I'm trying to contextualize this for you, try to show you that there are reasons we do these things, okay? Okay, so therefore, let's write down Newton's law. Newton's law now says that the acceleration, which now I'm going to write as the derivative of the velocity with respect to time, making note of your critique of this problem, is equal to, well, negative gk hat, that's the force of gravity down with an acceleration of g, right, minus magnitude of v, minus the magnitude of v, not the magnitude of v, minus v vector, I apologize, it's now v vector, times the drag coefficient divided by m. Is that cool? Now, the gentleman with who talked to me before, okay? I want to engage you in this part of the conversation. Because you asked an interesting question. You said, why did I use L before? Okay? I'm going to ask you to do a dimensional analysis, a unit analysis. Remember, this is a velocity, okay? So what are the units of the left-hand side of this equation? Velocity is, meters per second squared, right? That's meters per second per second. Meters per second squared. G has units meters per second squared. Okay? Okay. V has units. Therefore, this coefficient must have units 1 over seconds. So therefore, the units of m over cd, which is the reciprocal of that coefficient, are time, or seconds. Okay? And this is called the drag time. And let me, like I did before, I defined that L before because I didn't want to have A and B running around with me all the time. Let me just call this tau, the Greek letter tau. It's some number, okay? Now, I want to tell you what the drag time is. Let's look at the drag time. The drag time gets bigger when the mass gets bigger. If the mass gets really big, the drag time is very big. If the drag coefficient gets really, really big, the drag time gets really small. So this tells you, by the way, that the drag coefficient has units kilograms per second. Kilograms per second, which is a weird unit, kilograms per second. In order for this whole thing to work out, because this is going to be kilograms, and this is kilogram. No, sorry. The drag coefficient, I got that wrong. The drag coefficient has units. Yeah, no, it has kilograms. Yeah, so I'm sorry, there's m is in meters and m is in mass. So this is meter. Let me write this meter, meter. You guys can get mad at me because I changed my notation. Meter, meter, meter per second, meter per second, meter per second. This is kilograms because this is mass. This comes from the mass. Yeah, so the drag coefficient is in units kilograms per second in order to get that ratio turning out to be a time scale. And now, everybody, we are left with the following equation. Yes, I did not solve it. I talked a lot about it. But I do actually want you to think about this. Okay? The solving is actually not that hard. We're left with the equation. Let v vector equal u of t I hat plus v of t j hat plus w of t k hat. These are the three components. Then I have du dt I hat plus dv dt j hat plus dw dt k hat. Those are the three components of the acceleration on the left-hand side equals negative u of t I hat minus u v j hat. I'm going to suppress v of t j hat minus w of t k hat divided by, that's this negative v over the drag time ta minus g times k hat. This is the problem I'm going to solve for you in detail next time. Everybody, you've solved the case. You've solved this problem. When ta goes to infinity, that is to say the drag coefficient goes to 0, you solve that problem. That's just a baseball. That's going to be parabolas. Okay, you guys know that that's parabolas when you throw a baseball in the air like that. I want to solve this problem for you when ta is not, when ta doesn't go to infinity. Okay? When c doesn't go to 0. This is like the parachutist jumping out of the plane or the ball flying through the air. This is going to give us a dragged trajectory. It's not going to be parabolas. And if you take a look at it, I would encourage you to look at it before you come on Friday. These kinds of equations look like exponential decay. There's an exponential decay hiding in here. And then there's a growth associated with this acceleration. Okay? That's the problem I'm going to solve in detail on Friday. See if you can solve it yourself beforehand.
Parameterizations.